In this video, we're going to study the Rijndael S-Box. Our goal is to understand the mathematical theory behind it and to implement it in code. Here's the table of contents of this video. First, we're going to talk about what the Rijndael S-Box is. Then we'll describe a bijection that exists between the non-negative integers and the binary polynomials, and we'll define what that means. Then we'll talk about multiplication of integers as polynomials, and again, we'll define what that means. We'll talk about modular reduction of integers as polynomials, and then we'll describe the construction of finite fields. Then we'll talk about the Rhino Multiplication and the Rheindel inverse. Then we'll talk about implementing affine transformations in code. And then finally, we can define the Rijndael S-Box. And then we'll write the code up. So first of all, what is the Rijndael S-Box? Well, the Rijndael S-Box is an S-Box that's used in the block cipher AES, the Advanced Encryption Standard. And we also call it, for this reason, the AES S-Box. So the AES algorithm is described in these PDF documents from NIST. But in this video, we're actually not going to talk about AES at all. We're just going to talk about the S-Box that's used in it. So here it is. To define it, why don't we define B8 to be the set of sequences of 8 bits. So the set of sequences of zeros and ones of length 8. And we can also think of B8 as a set of integers between 0 and 255. Or we can also think of B8 as the set of pairs of hex characters. Now, the Rijndael S-Box, it's a certain bijective function defined from B8 to B8. And this is the point of the video. We're going to talk about it. And if we look at it in terms of hex characters, the Rijndael S-Box can just be thought of as a function which takes a pair of hex characters to another pair of hex characters. So for example, in this table here, 9a gets sent to B8. And the way you interpret that is you have the 9 determines the row and a determines the column. So 9a leads to B8. And the goal of this video is to write code that reproduces this table right here. That's the point. So that we're going to start off by defining a bijection that exists naturally between non-negative integers and binary polynomials. And what do I mean by binary polynomial? Just a polynomial whose coefficients are 0 and 1. Why don't we define F2 to be the field of two elements? It only consists of 0 and 1. So a binary polynomial is just a polynomial with coefficients in F2. To refer to the polynomial ring, why don't we introduce an indeterminate variable t? And we'll write F2 of t to denote the ring of polynomials with coefficients in F2. So the elements in F2 of t are polynomials in t. And that means they're summations of powers of t with coefficients in front. Since the coefficients is either 0 or 1, it kind of makes it easy because when the coefficient is 0, it basically just wipes out the entire term. And we don't even have to write the t. And when the coefficient is 1, we definitely have to write the power of t, but we don't have to write the 1, right? So for what's a typical example in the polynomial ring F2 of t? How about this one? F of t equals t to the 8 plus t to the 4 plus t cubed plus t plus 1. We'll actually see that polynomial come up later. So just to introduce a notation, why don't we write n0 to be the non-negative integers, so 0, 1, 2, etc. Usually you write n for the natural numbers, a set of positive integers. So why don't we just write n0 for the natural numbers with 0 added to it. Now, given any non-negative integer x, that's non-zero, at least, we can write it as a binary expansion, right? With sum of powers of 2, with the leading coefficient being not equal to 0. In other words, it's equal to 1. So we can write x as a summation from I equals 0 to m of bi 2 to the I. Writing as a sum of powers of 2. And each bi is either 0 or 1, so each bi is in F2. And since we assumed x is non-zero, we know there is one B value, which is equal to 1. And that's called the most significant bit. The last bit value that's 1, that's the most significant bit. And B0 here is the least significant bit. Now here's the big idea we're going to think about and implement. We can use these binary coefficients, these BI, as coefficients of a polynomial. So given x, we think about its binary expansion, and then we associate to x the polynomial fx of t in f2 of t, where we just define fx of t be the sum from I equals 0 to m of bi t to the I. So the powers of t to the I are there, and then we have these coefficients of bi in front of it. And note that the number of bits of x is related to the degree of this polynomial. They're not exactly equal to each other, but they're up to 1 plus 1, they are equal. The number of bits is equal to 1 more than the degree. So notice the number of bits of x here is m plus 1, because we're going from 0 to m. So the number of bits is m plus 1, whereas when we look at the polynomial definition there, fx of t, we see the highest power of t is t to the m, right? So the degree of the polynomial is m. And in the case of x equals 0, we'll just define the associated polynomial to be the 0 polynomial. And that way, we get an association for every non-negative integer. So just to see a little example, why don't we take 201 in base 10? And what is the polynomial associated to that integer? Well, first, let's just convert x to binary. So that turns out to be 11001001. And so the polynomial formed is just the polynomial obtained by using those binary digits as coefficients. And we end up with this 7th degree polynomial here. Notice that, like we were saying before, the terms with the coefficient of 0, they can just be ignored. And the terms with the coefficient of 1, they need to be kept, but we don't need to write the 1. So we get this 7th degree polynomial here, t to the 7 plus t to the 6 plus t cubed plus 1. So 201 is associated to that polynomial, that 7th degree polynomial. And in this manner, we actually get a map, a function, from the set of non-negative integers into the set of binary polynomials. And we associate x to fx of t, and that's a bijection if you think about it. It's a one-to-one and onto function. We won't go into it, but you could even say more. You could say phi is an isomorphism of commutative rings. But before you could do that, you would need to supply an addition and a multiplication on the set and n0. And those operations couldn't be the normal addition and normal multiplication. We're going to actually define a different addition and multiplication than we're used to. The addition operation that we're going to use is not normal addition, but XOR. And we'll write the symbol, a circle with a plus sign for that. And notice that if you take x, XOR y, and think about the associated polynomial, that's the same as if you did fx of t plus fy of t in the polynomial ring f2 of t. So that's a nice little relationship. And generally, if z is a summation of many xi's, XOR summation, then the associated polynomial fz of t is the summation of the fxi of t. And we'll use that little fact later. Another property is that if you look at x and you left shift it by 1, and then you look at the associated polynomial, that's the same thing as taking fx of t and just multiplying it by the variable t. So left shifting by 1 on x, that associated polynomial is just obtained by multiplying the original polynomial fx of t by t to the power of 1, just by t itself. So we can easily prove that here. If x is represented by the binary digits bm to be 0, then when you left shift it by 1, you just put a 0 in the far right side there, right? And then the associated polynomial through those coefficients is just that summation. You can ignore the I equals 0 there because the coefficient is 0. And then you factor a t out to the front. And then you see the summation indices are the same. They're I minus 1 on both. And then you just shift the indices down by 1. So then you get t times the sum from I equals 0 to m of bi t to the I, which is t times the associated polynomial fx of t. And then if we repeatedly apply this, like keep left shifting by 1, let's say we left shift by I, we see that the polynomial associated to x left shifted by I is just equal to t to the I times the original polynomial fx of t. And we'll use this fact later too. All right, so in the next section here, multiplication of integers as polynomials. Just to motivate what we want to do here, why don't we make up two integers, 201, we saw that one before, and 102. We'll write them each in binary, and then we'll think about the associated polynomials for each of them. The one associated to 201 is a 7th degree polynomial. The one associated to 102 is a 6th degree. And then we're going to multiply these polynomials. Here we go. I'll spare you the details. We get a 13th degree polynomial back. And that 13th degree polynomial corresponds to that bit sequence. And in base 10, not that it matters, is 10,710. So our goal of this section is to write a little Python function. We want to multiply integers as if they were polynomials in f2 of t. So imagine we're given two integers x and y, non-negative integers, and we look at the associated polynomials fx of t and fy of t, and we multiply them, and then we call that product fz of t. We want to write a Python function which returns that number z. So in that last example we did, if we put 201 and 102 in for x and y, we would like the function to return 10,710. And notice this is not normal multiplication here, because normally when you multiply 201 by 102, you get like 20,000 something. And just to emphasize here, the inputs to this function are not polynomials, and the output is not a polynomial. The inputs and outputs are all integers. In order to write this function, we're going to have to understand how to multiply these two polynomials, fx of t and fy of t. To do that, let's expand fx of t into powers of t. So let's write fx of t as the sum from I equals 0 to m of bi t to the I. Then fxt times fy of t would be what? Well, we're going to leave fy of t alone, but let's replace fx of t by that summation from 0 to m of bi t to the I. And then let's distribute the fy of t into the brackets so that we get the summation from I equals 0 to m of bi t to the I fy of t. And then let's remember that bi is either 0 or 1. If it's 0, that coefficient bi equals 0 just eliminates the entire term and we can forget about it. And when bi is equal to 1, that term definitely needs to be kept, but the bi equals 1 in front doesn't need to be written. So we can write this as a summation over all I, where bi is equal to 1 of t to the I fy of t. And then we remember that little property that if we have t to the I fy of t, that's the same as the polynomial associated to the left shift of y by I times. So we can replace that and we get a nice little formula for the product of those polynomials. We see that at the bottom. fx of t times fy of t is the sum over all I, where bi is 1, of the polynomials associated to y left shifted by I. And remember that other little property that if z is the summation of these xi's, then the associated polynomial to z is the summation over I of the fxi of t. And let's use that property right now. Let's define z to be the summation of these left shifts of I. And then the associated polynomial fz of t, as we can see here, is the summation of all those polynomials associated to those left shifts, which, as we saw on the previous side there, is fx of t times fy of t. So we've just actually derived a formula for the number z to find the z such that fz of t is equal to that product. Z is the summation of the left shift of y by I over those I where bi is 1. And that's our formula we want, and that's what we need to implement in code. And here we go. So let's say we're given x and y. If x or y is 0, we'll just return 0. So that's not an interesting case. And otherwise, let's assume that both of them are non-zero. And what we're going to do is cycle through the bits of x. And we do that with the while loop, right? Notice on line 5, while x is non-zero, and then we do some stuff, and then on line 9, we shift x to the right by 1. And that way we're going to process the least significant bit each cycle of the loop. And the way we access the least significant bit is we do x and 1. So on each cycle of the loop, we access the least significant bit by doing x and 1. If it's equal to 1, then we add on the current value of y onto our running sum of z, which is initialized to be 0. You know, instead of left shifting y, the original value of y by I times each cycle of the loop, what we do is we just move y by 1 to the left each cycle of the loop and update it like that. So we don't keep the original value of y. We just updated each cycle of the loop. And that's the same thing as shifting the original value of y to the left by I units. And when x eventually becomes 0, then we're done. And the value of z is what we're looking for. Now we're going to do something similar, but instead of multiplying, we're going to write a function that simulates modular reduction of integers as polynomials. So just to see what we mean, let's do an example again. Why don't we take that 13th degree polynomial that we just saw, we'll call it f of t, and then we'll define that polynomial m of t that we saw earlier to be t to the 8 plus t to the 4 plus t cubed plus t plus 1, that'll be m of t. And notice f of t corresponds to that binary sequence, which in base 10 is 10,710. And m of t corresponds to that binary sequence, which is 283 in base 10. Now we want to reduce f of t by m of t. And we're going to show the algorithm to do that here. It's pretty easy to see how to do it. We first notice that the degree of f is greater than or equal to the degree of m, so we know that f is not fully reduced. And our goal is to eliminate the highest power of f of t using m of t. To do that, we subtract the degrees, so we do 13 minus 8 to get 5. And so the way we're going to eliminate the power of t to the 13 in f is to subtract off from f t to the 5 times m of t. When we do t to the 5 times m of t, we get a 13th degree polynomial. And then when we subtract them, the powers of t to the 13 are canceled off, and f of t gets smaller in degree, and that's the whole point. Now, since we're in f2, though, addition is the same as subtraction. So instead of writing minus f of t minus t to the 5 m of t, we'll just write f of t plus t to the 5 m of t. So when we calculate that, I'll spare you the details. We get an 11th degree polynomial. So we started with the 13th degree, and we knocked it down a little bit on step 1 to an 11th degree. And that's our new value of f of t. And then we just keep going like that. We look at the degrees. The degree of f of t is still greater than or equal to the degree of m of t. So we subtract those degrees. 11 minus 8 is equal to 3. And so we calculate f of t plus t cubed times m of t this time. And then the powers of t to the 11 cancel off this time. And we end up with a 9th degree polynomial. So we're making progress. The degrees are going downwards. But still, the degree of f is greater than or equal to the degree of m, so we're not done. We subtracted degrees. 9 minus 8 is 1. So on our next round, we need to calculate f of t plus t times m of t. And we end up with this 6th degree polynomial. And now we're done because the degree of f of t is 6, and that's less than the degree of m, which is 7. And so we're done, and that's our final answer. And in base 10, that would be 88. And so we want to write a Python function which will calculate that number for us. So let's write a function called mod_int as polynomial that takes in two integers x and m, not polynomials, just integers. And we want to find the function, we want to find the integer z such that fz of t equals fx of t modded down, modded reduced by fm of t using polynomial reduction. So we expect that if we put 10,710 in for x and 283 in for m, we should get 88 out, right? We'll test that later. And notice this is not normal modulo reduction. Normally, if we take 10,710 and mod it by 283, we get 239. So we really are defining some new operations here. So as illustrated in this example, the algorithm to reduce fx of t by fm of t is what? Well, we first initialize a variable that'll go through the loop. Why don't we call it f of t to be fx of t? And then each time in the loop, we just ask ourselves, is the degree of f less than the degree of f of m? And if it is, then we're done. And we return f of t as the result. That's the reduced polynomial. Otherwise, we define d to be the difference of the degrees. And then we redefine f of t as f of t plus t to the d fm of t. So our goal is to translate this algorithm, which takes place in the polynomial ring. We need to translate that back into non-negative integers where our code takes place. Well, notice that the number of bits is essentially the same as the degree, right? Remember, the number of bits of x is the degree of the associated polynomial fx of t plus 1. So that condition that the degrees be less than each other is the same as the condition that the number of bits be less than each other, right? Those are equivalent. So we could rephrase the statement about degrees in terms of the number of bits. And also when we subtract the number of bits, notice when we replace the number of bits by the degrees there, how those plus 1 and cancel off here. We have a plus 1, then a minus plus 1. So that means the difference of the bits equals the difference of the degrees. So when we define that integer d as the difference of the degrees, that's the same as the difference of the bits. So we can make that change as well. And then that variable, that polynomial f of t, if we pretend that is associated to z, a non-negative integer z, so that f of t is equal to fz of t, then what is our new polynomial going to be? Well, if we have fz of t plus t to the d fm of t, then how can we write that in a different way? Well, we know that t to the d times fm of t is m left shifted by d, the associated polynomial to m left shifted by d. So we make that change. And we know that when we add two polynomials in the polynomial ring, it's the same as the XOR operation back in the non-negative integers, right? So we see that our new polynomial is the same as the polynomial associated to z XOR m left shifted by d. And that's all we need to translate the algorithm into the world of integers. So given integers x and m, non-negative integers, the algorithm will be this. We'll define z to be x. If the number of bits of z is less than the number of bits of m, then we stop and we return z. Otherwise, we define d to be the difference in the bits, and then redefine z as z XORed with m left shifted by d. And eventually, our break condition will occur. The number of bits of z will eventually be less than the number of bits of m. And then we break out and return z, and that'll be the result we're looking for. So the first thing we need to do is to define a function which gives back the number of bits of x, the minimal number of bits that x takes. So if x is 0, we'll just return 1 because to store 0 requires 1 bit. That's not the interesting case. So let's assume x is non-zero, and we'll just define the number of bits to be 0 and as a running sum. And then we just cycle through the bits of x. We kind of saw that technique before. While x is non-zero, we right shift x by 1, and that's the way we cycle through the bits. And each time we go through that loop, we increment that running sum number of bits nb. Eventually x will become 0, and then nb will be the number of bits. And we return that. And now we can implement that algorithm that we just discovered. So to write this function mod int as polynomial, which takes in x and m, the number of bits of m is defined to be nbm. That'll stay the same throughout the entire loop. But instead of introducing another variable z, why don't we just reuse x? And so a typical cycle through the loop will be like this. We'll define the number of bits of x to be nbx. If the number of bits of x is less than the number of bits of m, as we saw, that means we're done and we return x. That's like returning z. Otherwise, we define the m shifted over, left shifted by how many positions? Well, the difference in the number of bits. And that's represented by nbx minus nbm. And then we XOR x, the current value of x, with that shifted value of m. And that's the way we update x. It's like updating z, but let's just reuse the letter x so we don't introduce another variable for no reason. And that's it. Now this section will be pretty heavy mathematically. And the reason I include it is to show that this Rheindel construction, which we'll see later, is just a special case of a much more general construction. And I think if we understand the more general perspective, then we'll understand the specific implementation of the Rhino Multiplication and the Rheindel field structure when we actually look at it later. For this section, constructing finite fields, just at the beginning here, let's imagine f is any field. It could be finite or infinite. And we'll associate the polynomial ring to that, f of t. Again, t is an indeterminate variable. There's just a few definitions that we need to review here. A polynomial f of t is called constant if f of t is equal to c for some c in f. And we'll call it irreducible if it's not a constant and you cannot express it as a product of two non-constant polynomials. So what that means is that f of t can't be written as a product of two polynomials, each having a positive degree. And the principal ideal is just all multiples of a given element. So if f of t is a polynomial in the polynomial ring, the associated principal ideal, which is just denoted with brackets around the polynomial, is just f of t times g of t, where g of t ranges over every possible polynomial in the ring. And that subset of the polynomial ring is called an ideal, and it's a principal ideal because it's generated by one element. Here's a little proposition that's useful. A polynomial is irreducible if and only if the associated principal ideal it generates is a maximal ideal. Just remember that a maximal ideal is a proper ideal, and the only ideals which contain it are itself and the whole ring. We also have a general result from ring theory here that if you have a commutative ring with identity, then an ideal I of R is maximal if and only if R mod I is a field. So if and only if the quotient ring is a field. And we can use that with R being the polynomial ring f of t and I being the principal ideal generated by f of t. And we see something interesting here that to any irreducible polynomial f of t, we can associate a field to it. The field is f of t mod out the principal ideal f of t, generated by f of t. And we want to look at this construction where we take the field f to be the finite field fp of p elements. Before we do that, though, let's just remember a really important theorem about finite fields. Let's say we have a finite field of cardinality q. Then necessarily q must be a power of a prime. So the only finite fields that exist have cardinalities that are powers of primes. For example, you could not have a field of cardinality 6, because 6 is not a power of a prime. So moreover, for any prime p and any positive integer n, up to isomorphism, there is one and only one field of the cardinality q, which equals p to the n. Cryptographers usually denote this unique field as gf of q, or gf of p to the n, where here gf stands for Galois field. And mathematicians, they usually write it as fq or fp to the n with a bold f. Now really, these notations, they refer to an isomorphism class of fields, not a particular field itself, right? The underlying set might be different, but the isomorphism structure is what's the same all the time. So the question arises, how do we construct a specific field in FQ, in the isomorphism class FQ, for a given value of Q? You know, in the case when n is equal to 1, that means Q is equal to P, and it's actually easy to construct a field in FP. We just take Z mod PZ. The integers mod P under addition and multiplication, that's a field of order P to the 1. So that's no problem. But when n is bigger than 1, how do we construct fields that have P to the n elements? So to introduce that construction, let's first just look at any polynomial f of t in the polynomial ring, fp of t. So the polynomials whose coefficients are in fp. Before we were looking at polynomials whose coefficients were in f2, right? So now we're speaking a little more generally. The polynomials here have coefficients in fp. And let's just take f of t to be any such polynomial of degree n. It doesn't have to be irreducible for this little section. So the observation that I want to point out is that if we look at the quotient ring with respect to that polynomial, the principal ideal generated by that polynomial, then a complete set of coset representatives of that quotient is given by the set of polynomials of degree less than n. So if we define C to be a subset of the polynomial ring to consist of all polynomials g of t whose degrees are strictly less than n, then every coset has a representative, a unique representative in C. And notice the set C is finite. A typical element in C can be written as a summation of powers of t. Since the degree of the polynomials are all less than n, we know the highest power of t is going to be t to the n minus 1. And so we get g of t to be that summation. The coefficients there, they go from b0 up to bn minus 1. There's n of those coefficients, right? And each of those coefficients are from the set fp, which has p elements. So that means in total there's p to the n such polynomials. And we see that the cardinality of that quotient ring is p to the n. So we're getting the right cardinality here. When we do that quotient ring, we get the right cardinality. And then if we put this together with what we saw before, is that if we take additionally our polynomial to be irreducible, then that quotient will be a field. So here we go. This is our construction. We take any prime p, any positive integer n, and f of t to be any irreducible polynomial in fp of t of degree n. So it has to be irreducible, and it has to be of degree n. Although we didn't prove it, there always exist irreducible polynomials of degree n for any n. Then the quotient ring is actually a field because f is irreducible. And since f has degree n, we know the cardinality of that quotient is p to the n. So there we go. We've constructed a field whose cardinality is p to the n. That's great. Now, just a small comment. Imagine we take two different irreducible polynomials and both of them have degree n, and we form both of those quotients. We actually get two fields, right? F1 and F2. Now, are these fields the same or not? Well, they have the same addition operation, but their multiplication operation could very well be different, right? Because we're modding out by different polynomials. But the point is that both of these fields are isomorphic because they have the same cardinality of p to the n. So even though these fields are slightly differently defined, they are both members of the isomorphism class FQ. So the code we've written allows us to find products and modular reductions of integers as if they were polynomials in F2 of t, right? So why don't we use our code and this general construction to realize fields of the form f2 to the n for any n? The elements of the field will just be integers from 0 to 2 to the n minus 1. And the addition is the XOR operation. And the multiplication is done by composing those two functions we've written. We're going to multiply the instance polynomials. and then modded down by m. And what is m here? We have to choose it so that the associated polynomial is irreducible and of degree n. And then we get a field structure on the set of integers from 0 to 2 to the n minus 1. In other words, the sequences of n bits, which has a different multiplication than we're used to. It's not mod multiplication mod 2 to the n. It's a different type of multiplication. And just a small comment is that since our code is written to work with F2, it actually can't be used for constructing fields in Fp to the n where the prime is not equal to 2. Now, the algebraic construction still works. It's just the code that we've written so far is specially written to work with F2. So as it stands, our code is not going to be able to construct fields other than F2 to the n. So let's finally talk about this Rheindel structure that we're going to put on B8. And what is B8 again, as we talked about before? It's just a set of sequences of 8 bits, which we can look at as the integers from 0 to 255. Now, B8 is the set of all possible bytes, right? Bytes, a byte is 8 bits, and so B8 is a notation for the set of all bytes. And really, the set of bytes is such an important set in computer science and cryptography. It's natural to ask if there's some type of algebraic structure we can put on that set, other than just being a set. And I guess the first natural guess would be to use addition and multiplication mod 256. And that provides it with the structure of the commutative ring, Z mod 256, Z. But the problem is that's not a field. And that's because there are non-zero elements which do not have a multiplicative inverse. In fact, any element that's not co-prime to 256 will not have a multiplicative inverse. So we can make B8 into a ring, no problem. But the question is, can we make it into a field? Can we put maybe some different definitions of addition and multiplication on B8, which makes it into a field instead of just a ring? And the first thing to notice is, what is the cardinality of B to the 8? It's 2 to the 8. And by our theorem on finite fields, we know there exist fields of order 2 to the 8. P equals 2 is prime, right? So if we take in our general construction there of any field of order F2 to the n, why don't we just take n to be 8 in that construction? And here we go. To construct a field in F2 to the 8, we can do it. The field elements of the field will be just the integers from 0 to 255. The addition operation is XOR. And the multiplication is the composition of those two Python functions that we wrote. And here, m and n, I still have to tell you what that is. It's any fixed positive integer. And as long as the associated polynomial fm of t is an 8th degree polynomial that's irreducible, we'll get a field structure. But the Rheindel multiplication, the Rheindel field structure, uses a very specific value of m. And we've seen that a couple times so far in this talk. M is going to be in base 10, it's 283. In binary, it's 100, 110001111. And as a polynomial, it's this 8th degree polynomial here that we've seen. It's t to the 8 plus t to the 4 plus t cubed plus t plus 1. And using that particular 8th degree polynomial, we're going to define a field structure on B8. So the Rheindel field structure on the set of bytes, B8, is really isomorphic to the field structure given by this quotient ring, which is actually a field, F2 of t mod out by that 8th degree polynomial. Now, if we took a different 8th degree polynomial, as long as it's still irreducible, that quotient will still provide another field structure on it, which will be isomorphic to the Rheindel field structure. But for what we're doing here, we really do need to use this specific polynomial. All of the Rijndael S-Box is defined with respect to this specific polynomial. So according to what we've done, just to write a function to implement this, if we put 201 and 102, those integers we saw before, when we multiplied those polynomials, we should get 88 back out, right? Because after we reduced down, if you remember, we got 88 out. Now, using the functions that we've written, it's really easy to implement this Rhino multiplication. We just define a function which takes two 8-bit inputs, x and y, defines z to be the product of those integers as if they were polynomials, but z is still an integer. And then m is that polynomial that we just saw, but we define it as a binary integer here. And then we mod z down by m. And the result we get out is the value of the Rhindel multiplication, and it's another 8-bit value. So we take two 8-bit values in, and we get an 8-bit value out. And so that's a binary operation. And it turns out that this binary operation, this multiplication that we just defined, provides B8 with the structure of a field. Every non-zero element now has a multiplicative inverse. Why don't we write a function to find the multiplicative inverse of a given value of x? To do that, we'll just implement it with a brute force search. And although x equals 0 doesn't have an inverse, let's just return 0 in that case, so that every input value has an output value. And if we're given a non-zero value, we'll just brute force search for every possibility from 1 to 255. And when we get a Rhindel multiplication of x times y equal to 1, we know we found the inverse, and we return that. All right, for the next section, we have to implement an affine transformation. So this is separate from what we've been talking about here. We just have to think about kind of a normal matrix equation here. A is going to be, capital A here is a 64-bit integer, but we're going to interpret it as an 8x8 matrix with coefficients in F2. So the binary expansion of it will have 64 bits, and each bit will represent an element in a matrix. So the first row of the matrix will be the 8 most significant bits, and the last row of the matrix will be the 8 least significant bits of A. The values of x and b are 8-bit integers, but we interpret them as 8x1 column vectors, and we're going to place the most significant bit at the top of the column. Now that we've interpreted these as matrices, we're going to evaluate them as a matrix equation ax plus b. That's what I mean by an affine transformation. When you send x to ax plus b, that's an affine transformation. And the value we get out will be an 8x1 column vector, but we interpret that as an 8-bit integer. So everything is inputted here as integers, but when we write the code, we're kind of thinking of them as matrices. Now to do matrix multiplication, we're going to need a dot product. So why don't we just write that function first? Let's say we're given two integers x and y, and we want to do their dot product. Let's think of x and y as sequences of bits. And just so they have the same number of bits, why don't we allow ourselves to pad the front of them with some zeros if we need to? And when we write x and y as the sequences of bits, the dot product of those will just be the XOR summation over all those bits of the individual bits applying the AND operation to them. So here the ampersand is the bitwise AND operation, and the O with the plus is the bitwise XOR operation. And then the dot product, to define that as a function, to start off, why don't we just do x and y? And then that's like ANDing all of the individual bits. If z is 0, we just return 0. Otherwise, we'll cycle through the bits of z. We've seen this technique already several times. While z is non-zero, we access the least significant bit of z, that's z and 1. And then we add it on, we XOR it on to the running sum of the dot. And then after z is 0, we know that we've ran through all the bits of z and we've XORed them all up, and we return it. And then we're ready to write our affine transformation now. Maybe the first thing to observe is to ask ourselves, if we're given this 64-bit integer a, how do we access the first row? The answer is we're going to take a and right shift it by 56 bits. And where I got 56 bits is I did 8 times 7 to get 56. How would you get the second row of a? Well, I would do 6 times 8 to get 48. I would right shift a by 48, and that would expose the 16 bits on the end. But I don't want all 16 bits. I just want 8 bits. So I AND it with 0xFF, which is 8 ones, right? So that's how I access any row. And I have to go in reverse, like from 7 down to 0. So that's why we're doing this reverse loop here. And once I grab the row, I just dot product with X and I get my bit. And then to place the bit in the right spot in my output Y, I left shift a bit over by I and then XOR it on the current value of Y. And that won't affect the other bits. And then to finish it off, I just add on B on the end. I just return Y XORed with B. After I get out of the loop, I have AX. And then to finish it off, I just return Y XORed with B. And we'll see that the Rijndael S-Box uses an affine transformation in it. And we're finally there. We can finally define what the Rijndael S-Box is. So as mentioned in the beginning, it's just a certain bijective function from B8 to B8. And S is actually defined as a composition. We first do a field inversion on B8, and then we compose it with a specific affine transformation that we will define in a second. Just for some notation, why don't we just define I to be that inversion function from B8 to B8? Remember that it sends 0 to 0. And for our specific, we'll define a specific integer A and B in a second. A is 64 bits, B will be 8 bits. And we interpret them as a matrix, 8 by 8 matrix in an 8 by 1 column vector. And then the Rijndael S-Box is defined to be S of X equals A times I of X plus B. So I of X is done first. You get a column vector. You multiply it by the matrix A, and then you XOR B onto that. And then you get the value of S of X. In those PDFs I mentioned at the start there, the affine transformation is described like this. This is the matrix A, and this is the 8 by 1 column vector B. And here the X0 and Y0 are the least significant bits. And for our approach, that's a problem. We need to rewrite it so that for our column vectors, the most significant bits are at the top. And to do that, we just reflect our matrices here as shown, a simple change. And then we can rewrite it so that equivalently, it's the same thing. Now the most significant bits are at the top. And in code, the way we're going to define A and B in Python is just like this. A is int of this string casted to a base 2 value. And here we go. Here's the Rijndael S-Box in code. We take an input X, that's 8 bits. And we first find the Rheindel inverse. We get an 8-bit value back. And then using the value of A and B we just talked about, we perform an affine transformation, not on X, but on X inverse. And the output of that affine transformation on X inverse is the value of the S-Box for a particular value of X. And to print out the table, you know, there's 256 values. So why don't we print it out using 16 rows, and on each row, there'll be 16 values, just like we saw in the table at the start. And when we'll need to format it in case there's just to put a leading 0 in front to make it look nicer. All right, so now let's write it in code from a blank file, and we'll just put it all together, and we'll see how we actually get a printout of the Rijndael S-Box, which was the point of this video. Let's open an empty file, and let's start to write out the code to implement the Rijndael S-Box. All right, the first function we have to write is multiply ints as polynomials, which takes 2 integers x and y as inputs. If x or y is 0, we just return 0. That's the trivial case. So when x is non-zero, we'll define a running sum, z, to be 0. And then we cycle through the bits of x, right? The way we do that is, while x is non-zero, we access the least significant bit, x and 1, do whatever we need to do, and then we shift the bits of x to the right by 1 at the end of the loop, and we keep going like that until x is 0. And what do we do inside of the loop? Well, remember that if x and 1, which is the least significant bit, if that's equal to 1, then we need to add on the left shift of y onto z, the running sum. And instead of left shifting the original value of y by I times, we just left shift y by 1 every time and call that y again. It's the same thing. And then eventually when x is 0, we've added up all the appropriate left shifts of y, and we have our result. The next thing we have to do is write a function for the number of bits of x. If x is 0, we'll just return 1 because 0 takes 1 bit to store. Otherwise, we'll define nb to be the number of bits, kind of like a running sum. And as long as x is non-zero, we know that x has some non-trivial bits in it. And we just increment nb by 1, and then right shift x over, and we keep going like that until x is eventually 0. And we pick up the number of bits in that way, and then we return it. We could do a little test. Let's just multiply the integers 201 and 102 and multiply them as polynomials. We'll call that function on those two integers and then print off the result. And as we saw in the example that we worked out, we should get 10,710. And we see that we get that when we run it. So that's good. That test confirms that that function is working. And we can also test the number of bits. Why don't we see how many bits the number 15 takes? And we're getting 4, and that's correct, right? Remember, 15 is 1111. So now we define the next function, mod int, as polynomial, and it takes integers x and m as parameters. Let's define nbm as the number of bits of m. That'll stay the same throughout the entire function. And then we'll enter a while loop, and we'll define nbx to be the number of bits of x. If the number of bits of x is less than the number of bits of m, we know we're done and we just return x. Otherwise, we define a shift of m. We define m shift to be m left shifted by the differing number of bits, so nbx minus nbm. And then we XOR m shift onto the current value of x, and then redefine x as that. And that really has the effect of eliminating the highest, most significant bit of x. And that will eventually make it so the number of bits of x will be less than the number of bits of m. And then we'll break out of the loop. And then just for a little test here, if we remember in our examples we did, if we took the polynomial that corresponds to 10,710 and then modded it by the polynomial which corresponds to 283, which is actually that Rheindel polynomial, then we got 88, right? And we can test that in and as a little test, and we see that we do get 88, so that works. Okay, now we can write the next function, which is the Rhino Multiplication, which takes in two 8-bit integers as its input. To implement that, we've really done all the hard work already. Just define z to be the product of those integers as if they were polynomials in f2, x, or t. Define m to be that Rheindel polynomial, that degree 8 irreducible polynomial. And then we just mod z down with respect to m. And the integer we get back is defined to be the product of x and y with respect to this new type of multiplication. And we can do a little example. If we multiply 201 by 102, as we saw, we should get 88. And when we run it, we do get 88. So that confirms our code is working there. And now let's write the Rheindel inverse function, which just takes in one input x. Although x equals 0, it doesn't have a multiplicative inverse, but let's just return 0 in that case. And that way, every input has an output. And then, in the case when x is non-zero, we just do a brute force search over every possibility from 1 to 255. And when we find a y value such that the Rhino multiplication of x and y gives 1, we know we found the multiplicative inverse and we return that value y. And just for a little test of that, let's make up a number x, let's say 99. Let's take y to be the Rheindel inverse of x. And what we hope is that when we multiply x and y with respect to the Rhino multiplication, we should get 1. So let's print that value off. Let's print Rhino multiplication of x and y, and we hope we get 1, and when we run it, we get 1. So that works. All right, let's define the dot product function, which takes in two non-negative integers, x and y. To start off, just define z to be x and y. That takes the and of each corresponding bit of x and y. If z turns out to be 0, just return 0. I wrote return z there, I don't know why. It'd be better to write return 0. And initialize our variable dot to be 0. And then just cycle through the bits of z. And access the least significant bit each time by doing z in 1. And then just XOR that onto the value of dot. That's how you take the XOR addition of all the bits of z. And then you just return the dot, the value of the dot product. We're going to have to write a function to do affine transformations, which involves a matrix multiplication. So writing a dot product function is worthwhile. So to implement the affine transformation, which takes in a 64-bit integer a, and then two 8-bit integers x and b, we return an 8-bit integer as well. But we're interpreting all these integers as matrices, right? Capital A is an 8x8 matrix, and x and b are column vectors, 8x1 column vectors. So let's initialize y to be 0. Y is going to be our output. It's an 8-bit integer, but we look at it as an 8x1 column vector. So I is going to range from 7 down to 0. That's what that reversed range does. And then each time we access the row, we do that by shifting A to the right by an appropriate amount. And then we AND it with 0xFF, which is just 8 ones. And that captures the appropriate 8 bits of A, which corresponds to the row of the matrix. And then we just take the dot product of that row with x, call that the bit. It's either 0 or 1. And then we left shift the bit value over by an appropriate number of units, I, and then we XOR it onto y. And doing that doesn't affect the previous bits of y. And then after we exit that for loop, we have the value of AX, the matrix A times X, and then we just need to XOR B onto that. So we return Y XOR B. So we're finally ready to implement the Rijndael S-Box, which takes in a single 8-bit integer x. To define this function, we first define x inverse to be the Rheindel inverse of x. And then we define that 64-bit integer a we talked about, and the 8-bit integer b, which provides the parameters for the affine transformation. And then the value of the Rijndael S-Box is the affine transformation with respect to a and b applied to x inverse. Not to x, but to x inverse. And that's the value of the S-Box at x. And then why don't we finish off now just by writing a little function to print out all the values of this S-Box. There are 256 values, and we'll just print the values in 16 rows and 16 values per row. So we'll just have variables row and column ranging from 0 to 15. And then define x to be 16 times a row plus the column. X will just range from 0 to 255, right? And then define the hex string to be the value of the Rijndael S-Box at x. And then we'll format it in case we need a leading 0 just to make the table print out nicely. We'll print out that hex string, and with the print function in Python, the automatic behavior is to go to the next line. So we'll just specify after it finishes printing, instead of that behavior, we want to just print out a space. And then after it exits out of that inner for loop, we do want to print out a space, a new line character. So we'll just call print without any parameters. And when we run it, we see that we get the exact same values that we saw in the table at the beginning of this video. So now we understand where these numbers come from. All right. Thank you for watching.